Alrighty, gang, welcome back. Today we are going to sort of finish the unit we've been grinding through this week, which is an introduction to integral calculus, so that we are ready to kind of move on and wrap up the semester by learning all about integrals and the things we can do with them, which is sort of the spirit that Calc 2 begins with. Let me grab a little bit more fresh paper here and we can get started. Many of you will be glad to know that the majority of the tests are graded. I'm in like the ends now. So if your name happens to begin late in the alphabet, then you got a little bit longer to wait. But about 3/4 of the tests are completely done now, which is lovely. I do want to talk a little bit about that because there's one or two notes that I think kind of need to be passed on. But first, let's do our title cards. This is MAC2311, section 004, which is a Calc 1 class, and today is April Fool's Day, April 1st, 2022. So today we're going to finish talking about FTC, which remember is the fundamental theorem of calculus. Actually, there's two fundamental theorems, FTC1 and FTC2. But before we get into that, we need to have a small word about academic misconduct. Fucking exhausted. Been getting up at like 4 a.m. every day this last week. It's killing me. Academic misconduct. Before I say what I'm about to say, I want to say you guys better than my other classes, which is nice. That always makes me happy, but not perfect. So there are a few things that I just want to maybe remind you of. I'm not at the moment planning to throw down the hammer at anybody on this, but I do know that at least 3 or 4 people cheated on this test. In most of those instances, it wasn't a landmark thing, like it's not going to take a grade from an F to an A or anything like that. But if, when I notice these things, I have a choice to make about whether or not to go after some sort of academic misconduct sanctions. And those sort of sanctions can take a C or a B straight down to an F and even a ZF, which can be really bad news. Don't mistake my leniency in this instance for acceptance. So the folks who I noticed cheated on this test are not folks that I had noted as cheating in the past. And most of those instances were not glaringly offensive, as in like, transcribed straight from Mathway without any thought put in. At least most of the things here that looked cheaty appeared to have some actual work at some places in the test, not like every question was just straight run through Mathway and copied over. But there were a few instances where I saw certain problems or things copied straight from Mathway. You guys know I have a smartphone too, right? And I've been teaching math for years. Of course I have PhotoMath and Mathway and Symbol Lab and Wolfram and all those things installed. I've been teaching online for like 2 years. So of course I run my own questions through those things and I see what the output looks like. There's a big difference between what a kind of organic solution looks like and a transcribed solution looks like. I'm not going to call anybody out. And like I said, so far, I'm not 100% done with the test, but so far, I haven't felt compelled to file any academic misconduct forms yet. I have filed several for one of my other classes, just over this last week for exam 2. And in both of those cases, it was because this was somebody who I had caught doing it on the first test and then continued doing it on the second test. I don't think I caught any of you guys straight up cheating on the first test. There were some things that were maybe a little sus, but nothing that I was like, oh, this is definitely obviously cheating. There are some things like that on this test. So what I just wanted to say with all the love I can muster is that I do notice when you cheat. And just because you don't get a love letter from Dan Rodkin saying, hey, you're going to fail this class because your professor caught you cheating, doesn't mean I didn't notice. It just meant that for whatever reason, I elected to not pursue sanctions this time. 2 tests left in the semester, right? Exam 3 and the final exam. If I see anything at all on either of those tests, I'm not going to send you an email or Canvas message. I'm not going to make a mark on your test to say, come talk to me so we can figure this out. I'm just going to file the letter with Rodkin and let the conduct board sort it out, because I don't have time to be doing this stuff. And it's really important that we preserve the value of your degrees. And the only way to do that is to make sure that, you know, the work is actually your own work. So like I said, I'm not going to call anybody out here and not planning to file any conduct reports so far based on what I've seen. But there were three cases here where I saw what was pretty clearly some cheating. I think I could win the conduct cases if I tried to, but I don't want to do that. I want to give you guys an opportunity to redeem yourselves and be honest throughout the rest of the term. And I know the majority of you have been through the whole term. So let me say that as well, like the people who have been strong and not done anything like that. I really applaud that. I know that takes a lot of discipline in this setting, and that's a really good thing. And to the folks who've had a moment of weakness and made a less than great decision in those ends, I understand that too, right? I'm sympathetic there. But do not do it again. All right, do not do it again. Another little note on the test, there were two problems that pretty universally everybody struggled with. Numbers 11 and 12. I think 11 was computationally just a bit intense. It seems like a lot of us kind of forgot how to hunt for horizontal asymptotes, exactly what the procedure is there. And so you can see the comments I left on your written work or elsewhere in the test for an explanation. And then taking those two derivatives and setting up those two number lines, it's a bit of work. It's a bit of work. So make sure you're really comfortable with the curve sketching stuff from section 4.5 before the final. Set aside a little bit of time, go back and practice some of those problems, including finding asymptotes, because that is an important part of that procedure. The other one a lot of folks struggled with was number 12, where we give a bunch of conditions on a function and we ask you to sketch a graph. And there again, the real sticking point seems to be the asymptotes. Most people did pretty well with the increasing, decreasing, and concave up, concave down parts. But coming up with a function that satisfied those conditions and satisfied the limit conditions from the first part, I had, I think, just one or two fully correct answers there so far. So those two problems were pretty universally challenging for everybody. And I'm applying not a curve, but a very loose standard of grading for those two. So I'm trying to grade those two gently. So you may think like, oh, you know, why did I get a 7 on this? I thought I was going to get like a 5. I'm trying to be as kind as I can on those two, because I recognize that number 12 is quite time consuming. Or sorry, number 11, the derivatives and number line stuff is quite time consuming. And number 12, it seems like we have a little bit of trouble remembering the rules for asymptotes. So let me just summarize these things. First, I know some folks cheated. Don't do that shit. Next time it goes straight to student affairs. So this is the one and only one warning. And then review horizontal asymptotes ASAP. Remember, a horizontal asymptote comes from a limit as x goes to infinity of f of x, or limit as x goes to negative infinity of f of x. So if you want to try and figure out horizontal asymptotes and you have the function in hand, you can take the limit as x goes to negative infinity, take the limit as x goes to positive infinity. If you get a straight up number for either of those, then those are your horizontal asymptotes. So I just want to encourage you to go back, review the definitions, practice doing some calculations. And yeah, don't cheat on future tests, right? If I see anything even vaguely sus on future tests, just going to send it off and let them handle it. But the majority of you were honest, and the majority of you did quite well. The possible exception of those two problems, one of which was time-consuming, and both of which seemed to hit on this topic, which it looks like a lot of us struggle to remember. So besides that, overall, very well done. We've been talking about these two theorems, FTCII, which says if f is continuous, and we define the function g of x to be the integral from a up to x of f of t dt, then g is differentiable. With derivative g prime of x equals f of x. And at the end of our last class, we spent a good deal of time playing around with an explicit function little f, calculating a bunch of values for the function little g, and trying to really convince ourselves that the derivative of g should be little f, that g acts like an antiderivative for little f. The other theorem that we've been playing with a bit, FTCII, says if big F is any antiderivative for little f, then the integral from a to b of little f of x dx, we have this kind of special notation for it, big F of x, with these, we call them evaluation brackets from a to b. Sometimes you'll see people not write the one on the left, just the one on the right. Sometimes you'll see people not write anything on the left and then just a vertical bar on the right with the a to b. But all of those notations mean the same thing. It's just big F of b minus big F of a. We're going to play a little bit with FTCII today. We've looked at some examples. I want to look at a couple more. And then we're going to see how the chain rule interacts with FTCII. That's something that can be a little challenging. To try and explain why the chain rule does what it does in the context of the first fundamental theorem, we're going to prove a special formula involving FTCII by using FTCII. And then the last thing we're going to do today is just grind out a few more examples of evaluating definite integrals using the second fundamental theorem. And that's really going to be the core of the class from here on out. Okay. Questions about the test? If you do have specific things you want to talk about, grade concerns or specific questions from the test, feel free to hit me up in the office hours with those. Let's look at a little warm-up problem involving FTCII and then introduce the chain rule. So let's let g of x be the integral from x up to 0 of 1 over the square root of t dt, and find g prime of x using FTCII. So this function g of x, it's the sort of function we were playing with at the end of class last time. It's the sort of function that FTCII talks about. The only difference here is that instead of having an integral from like some number up to x, I have the integral from x up to some number. So my first step here is going to be to rewrite g of x in a fashion that is a little bit more like what we see in FTCII. By applying one of those properties for the definite integral. That is, I can change the bounds from x to 0 into 0 to x. I can flip those over by popping a negative out. And then everything else stays the same. So by FTCI, g primed of x, this negative is this negative here. And then FTCI just says, take this variable and plug it into the function in here. So this would be negative 1 over the square root of x, or just negative 1 over root x. That's all. So that's our warm-up. FTCI really just says if you want to differentiate something like this, you just take this function inside and plug this variable into it. In other words, the derivative gets rid of the integral. Differentiation and integrals are inverse operations, and that's why the antiderivative is so relevant for FTCII. To see how this thing plays with the chain rule, I'm going to let u be u of x be a differentiable function of x. And compute g primed of x, where g of x is the integral from some constant a up to my function u of x of f of t dt. The way I'm going to do this is by using the second fundamental theorem to find another expression for this guy, and then differentiating through that. And what you'll see is that the output is very similar to what FTCI suggests, but with an extra little term slapped on. So by FTCII, if big F is an antiderivative for little f, then g of x, which is the integral from a up to u of x of little f of t dt, should be big F, I guess big F of t if we're being careful, evaluated from a up to u of x. Here's a t, which would be big F of u of x minus big F of a. So g primed of x would be big F of u of x minus big F of a, all primed. The f of a piece is going to differentiate to 0. A is just a constant, so f of a is just a constant, so the derivative of that constant is 0. The fun happens over here. We use the chain rule. This would be f primed of u of x times u primed of x by the chain rule, and then minus 0 from this guy. But f primed is an antiderivative, sorry, big F is an antiderivative for little f, which means big F prime is little f. So this is little f of u of x times u primed of x, like so. And this is the, oh, sorry, go ahead, Sean.
Why is f of a considered 0? Is it a constant always?
F of a is a constant, so the derivative of that constant is 0. Yeah, remember in FTCII, when we talk about this function g of x, it's the integral from some constant up to your variable, right? So this a down here is a constant, which means the a here is a constant. So we're taking my antiderivative, big F, and plugging in a constant. When you plug a constant into a function, you get a constant. You know, think of a as like 3 or something. This is big F of 3. So
Thank
that's
you.
and then when I differentiate it, yeah, I'll get 0. All right. So sort of the piece to remember here is that if g of x is something like this, then g primed is going to be this. In other words, you apply FTCII like normal, taking the upper bound here and plugging it into this function, right? Integral goes away. Take the upper bound, plug it into your function. That would be this. But then by the chain rule, you need to multiply by the derivative of that upper boundy thing, because that upper boundy thing isn't just x, it's now some function of x. Let's try a couple examples. I don't mind telling you that at least one of these shows up on exam 3 pretty much every time. And the difference between like a 7 out of 10 on this question and a 10 out of 10 on this question is understanding how to use the chain rule appropriately. So I want to calculate g primed of x, where g of x is the integral from 1 to x squared of cosine of e to the t dt. Normally what FTCII says is if you want to differentiate this thing, you would just take this and plug it in for the variable here. But this is not just an x, it is a function of x, non-identity function of x. So what we're going to do is follow the recipe from the chain rule. It says take that variable upper bound and plug it in for the variable here. So I'd get cosine of e to the x squared, but then multiply by the derivative of this thing. This is little f of u of x times u primed of x. Like we just proved on the previous page. And then, of course, the derivative of x squared is 2x. So I could write this as 2x times the cosine of e to the x squared. Let's try one more. Again, I've got a function defined as an integral from some constant up to some variable. My little f of t is the square root of t cubed plus 1. A is pi over 2. U of x is sine x. So when I go to differentiate this, I should get my function little f, but with this plugged in for t. So that's the square root of sine cubed of x plus 1. And then I have to multiply by the derivative of the u function. The derivative of sine is cosine, so I can write this as cos x times the square root of sine cubed of x plus 1. Starting to get a reasonable feel for it? Starting to feel comfy? Okay, good. Let me try one more with a slightly different notation. My wife just came home and closed the door, so I'm on the baby. Try one with a slightly different notation because, we keep calling this thing G and we keep saying find G prime. There are other ways to phrase these questions and that can throw people off too. So I'll do just one more and then we'll call it a day. And let's mix up all the good stuff here. Let's calculate d dx of the integral from x up to x squared of 1 over the natural log of t dt. So certainly this looks different. But the ideas are the same. What I have here is the function that we could call g of x. And I've been told to differentiate it with respect to x. So this is the same thing as saying, let this thing be g of x, find g prime of x. It's just written differently. Of course, the other big difference is that I don't have a constant down here. Sorry, my son. I don't have a constant down here. I have a variable in both the lower and upper bounds of integration. So we're going to need to do a little bit of work. Remember one of those rules we discussed the other day, one of those properties for integrals, is that the integral from a to b of, I'll say f of t dt, can be written as the integral from a to c, f of t dt, plus the integral from c to b, f of t dt. We used this in our last example on Wednesday to split up an integral, like when we did the integral from 0 to 4. To find g of 4, we said, oh, that's the integral from 0 to 3 plus the integral from 3 to 4. This is a not often used, but very useful property of the definite integral. I can use that to split this integral up. I can say that, so I've got my ddx up front, this ddx is this ddx. And then the integral from x to x squared, I could split up as like the integral from x to 1 over ln t dt, plus the integral from 1 to x squared. So I'm thinking of x here as being a number larger than t dt. I'm imagining that 1 is a value of x, or is a value between x and x squared. It doesn't need to be between them. You can split it. I could have used a 0 here or anything really. So then I can take the derivative of each of these pieces separately. I'm realizing now that 1 was a bad choice, but not for any reasons I think anybody here will detect. So I'm gonna let it slide. The integrand isn't defined as 1, but that's okay. And now each of these is like a regular FTC1 problem. Right, this guy is FTC1 with the chain rule. And this guy is like FTC1, but first I need to flip over the bounds. Sorry, this says ddx of, I'll put the negative up front, negative ddx integral 1 to x, 1 over a natural log of t dt plus ddx integral 1 to x squared, 1 over natural log of t dt. So like we did on that very first example, I need to flip the bounds over here in order to make this look more like something from FTC1. So the integral from x to 1, I rewrite as negative, here's the negative, integral 1 to x. And I pop the negative out past the ddx. Now in the first guy, I apply FTC1. And the second guy, I apply FTC1 together with the chain rule. So this is like G primed. So this would be, I just need to take this x and plug it in here. So this will be negative 1 over the natural log of x from the first guy. Plus, using FTC1 together with the chain rule in the second piece, I get 1 over the natural log of x squared times the derivative of x squared. And this is the step where we're using the fundamental theorem. From here, we just need to compute that little derivative. So this is negative 1 over the natural log of x plus the derivative of x squared is 2x. So all right, that is 2x over the natural log of x squared. And this would be fine. This is good. So this last one, this is about as hard as these problems will ever get. Questions on what we've done here and why?
Yes. Why don't you use the chain rule on the first one?
I don't need to, because the upper limit of integration here is just x, not some function of x. Or if I did, if I was multiplying, if I was using the chain rule, I would multiply here by the derivative of x, but that would just give me a 1.
Got it.
Cool, cool.
Quick clarification on the rule that you wrote. Shouldn't it be A to C and then A to B and then B to C?
No, A to B and then A to C and B to C. Let's take a look at this because we only kind of mentioned this en passant. Let's look at it in its own right. Before I do that, any other questions on this one? Okay, let's go ahead and take a quick peek at that property. This is also a good time to share some symmetry properties with you. So final properties of the definite integral. Final times. So one of these is that the integral from a to b of f of x dx can be split up as the integral from a to c f of x dx plus the integral from c to b of f of x dx. And usually we think of the number c as a number between a and b, but it doesn't have to be. So you could actually be any number. I'm going to list a couple others here. If f is an odd function continuous on the interval negative a to a, then integral negative a to a of f of x dx is 0. That can be a big time saver. You notice that you're integrating an odd function over a region symmetric about 0, then integral is 0. You don't even have to compute it. This next one is also a time saver. If f is an even function, continuous on the interval negative a to a, then the integral from negative a to a of f of x dx can be simplified a little bit by writing it as 2 times the integral from 0 to a of f of x dx. So these items here, 2 and 3, are often called symmetry properties of the integral. All 3 of these are proved best through pictures. And I think the proofs for 2 and 3 I can squeeze into the margins here. So I'll just do that. I'm just going to sketch here a nice generic odd function. If you're going to integrate such a thing over an interval like negative a to a, so suppose negative a is here, and a is here, then we're talking about this area beneath the horizontal and this area above the horizontal. Remember, an odd function is one whose graph is symmetric about the origin. So for every little piece of positive area over here, there's a little piece of negative area over here that is exactly the same size. So this area and this area are the same size, but the integral measures this one as negative because it's beneath the x-axis. This one measures the area as positive because it's above. So they cancel. That's the idea. They cancel perfectly. The little picture proof for item 3 is also very straightforward. I take your sort of generic even function. Imagine integrating it from maybe all the way over here to all the way over here. So negative a is right here, positive a is right here. Then the total area is equal to double the area on the interval 0 to a. And that's the whole argument, right? If you're going to integrate from negative a to a, that's trying to get all of this stuff, you might as well just integrate from 0 to a and then double that answer because of the y-axis symmetry that even functions possess. You might ask, why would you do this? What's the difference? It's going to be the same amount of work to compute this integral as it is to compute this integral. Well, not exactly. According to FTCII, you'd need to find an antiderivative, plug in the bounds, subtract. 0 is one of those numbers that's always nice to plug in, right? Plugging 0 into an expression, generally an easy thing to do. So this saves you trouble at the evaluation step at the very end of your integral problem. This saves you having to even find an antiderivative, right? This does the whole thing for you in one swoop. Both of these are quite useful. The proof for item 1, I'm going to need a little bit more space. We might be able to try to tuck it in over here, but so it says if you're doing the integral from a to b, you could do the integral from a to c and then add that to the integral from c to b. I'm going to take a nice generic function f. Mark off some A's and B's. Definitely the integral from A to B is all of this area. Good enough. So I'll say that the pencil shaded area is the integral from A to B, f of x dx. And then I'm going to try to argue using some geometry. Let me plot my favorite number C right in here. The black pen shaded area here is the integral from A to C. And the red pen shaded area is the integral from C to B. So if you add the black area to the red area, do you get the pencil area? Yes, you do. Yes, you do. That's it. That is equivalent to the statement that the integral from A to B is equal to the integral from A to C plus the integral from C to B. Now, the fun part here is to try and convince yourself that this still works if I take C and I put it out here. If C is not between A and B, this still works. And that's a little more subtle. It's a little more subtle. So I'm not going to go through the separate, you can consider a total of 3 cases. One where C is to the left of A, one where C is between A and B, and one where C is to the right of B. We've shown here that when C is between A and B, this works well. Try to prove that this works, still works, if C is larger than B. And then the case where C is less than A, where C is off to the left, you'll see it's the same thing. But I'm not going to spend class time on that. Generally, when we make these sort of splits, we're assuming that C is between A and B anyway. That is a fun fact that you can do that even if C is not between A and B. Okay. The even and odd, the symmetry principles, these make for really good true-false questions on exams. Just a little hint or a nudge there. These make for excellent true-false questions. All right. Last thing I promised we would do today, and what we're going to do for the rest of the class time here, is just use FTCII to crunch out some integrals, because that is where we are going. That is what we will be spending our time doing with the remainder of the semester. We will just develop more and more techniques. And I want you to practice using good notation. Right, so that's the class. Something I see a lot in Calc 1 is folks being sloppy with notation, right? Not really too concerned about what symbols are on the page if they get the right number at the end. Do yourself a really solid favor and get in the habit of using good notation now. About half of Calc 2 is going to be you learning how to solve harder and harder and harder integrals. And if you develop bad habits here, they're going to be very hard to break. What I mean by good notation, good habits, always write your integral symbol until you've found your antiderivative. Always write the dx or dt at the end. Never skip that shit. If your integrand, the thing inside the integral, has multiple pieces separated by addition or subtraction, put that motherfucker in parentheses. These are the most important bits of notation that will really screw you over if you get in the habit of not using them, and will really help you if you get in the habit of doing them. So that rant out of the way, let's crunch some integrals. We can start gently enough. How about how about something like this? Off the top of my head, I do not know what the graph of that function looks like. I'm not going to try to draw or shade anything. I'm not going to use any Riemann sums or limits. I'm just going to use FTCII. Oh, see, I did something here that's illegal, didn't I? I didn't write the dx. Sorry. So FTCII says you want to do an integral, a definite integral from a to b of some function. Find an antiderivative for that bad boy, and then plug in these bounds and subtract. So what I need first here is an antiderivative. This is going to be equal to evaluation bracket, antiderivative in here for this thing, and then evaluated between the bounds. Each of the antiderivatives in this case is just a straight power rule thing. So who has derivative x cubed? What's an antiderivative for that? Well, that's 1/4 x to the 4. You differentiate x to the 4, you get 4x cubed. The 4 and the 1/4 cancel, you get x cubed. Minus antiderivative for 2x. Well, x squared has derivative 2x. Again, it's a power rule thing. I'll write it like this. All right, so you add 1 to the power, divide by the new power. The 2's are going to cancel. And then an antiderivative for 3 would be 3x. And I need to evaluate all this from 0 to 1. It's good to be in the habit of cleaning up your antiderivative before plugging in, before doing the evaluation. So I'd write this as 1/4 x to the 4 minus x squared plus 3x from 0 to 1. And then I will plug in the upper bound, which is 1. So 1/4 times 1 to the 4 minus 1 squared plus 3 times 1 minus, plug in the lower bound, 1/4 times 0 to the 4 minus 0 squared plus 3 times 0. So this is like big F of B minus big F of A. This whole apparatus here is 0. And 1 to the 4, 1 squared, those are all just 1. So this is 1/4 minus 1 plus 3, which is 1/4 plus 2. 2 is 8/4. So 1/4 plus 8/4 is 9/4. Every time you encounter a definite integral that you're going to solve the normal way, your workflow should look like this. All right, it should look like integral, antiderivative with evaluation bracket, simplify antiderivative, plug in bounds, simplify, simplify. Sometimes you want to do some more work before calculating your antiderivative. We saw that on Wednesday, right? We're finding an antiderivative. Sometimes you want to do some algebra first. You need to clean up the function inside to make it easier to see what the antiderivative will be. We'll look at a couple of examples like that. First, any questions on this one? Okay. Another good thing, getting in comfortable using different variables. We talked a bit about dummy variables the other day. The x in the previous integral, like the z in this integral, is a dummy variable. Could be whatever symbol you want. In the previous problem, we were integrating a polynomial. In this problem, I am integrating a polynomial. It's a product of two factors, but it is still just a polynomial. So at the end, we'll be using a power rule. But before I can take my antiderivative here, I need to do something else. What do I need to do before calculating an antiderivative?
Can you FOIL it?
Yeah, we need to distribute this out because you can't anti-differentiate this piece and anti-differentiate this piece separately. Antiderivatives, like regular derivatives, play nice with addition, subtraction, and multiplication by constants, but they do not play nice with multiplication of functions. So you gotta expand this out first. So I'll write this as the integral from 1 to 2. Z squared times z is z cubed. And then I'll have minus z squared plus z minus 1. And I've got multiple terms separated by addition or subtraction, so I put the whole integrand in parentheses, always writing my integral symbol, always writing my differential, always writing my bounds. It's good notation. Now I can crunch out the antiderivative. Again, it's just a power rule thing, so I'll add 1 to this power and then divide by that new power. Same thing for the z squared, I'll get minus 1/3 z cubed. Same thing for the z, I'll get plus 1/2 z squared. And an antiderivative for 1 dz is just z. Another little word of warning, when you integrate a constant, a lot of people have it in their head that you get that constant times x. That's not the whole story, right? It depends on what your variable is. You get your variable. So if you wrote a minus x here, that would technically be incorrect. I would understand why you did it, but I would still need to take off a half point or so.
Can you quick repeat that last bit right there that you just said?
Oh, sure. So really what I'm saying here is that the integral of 1 dz from a to b is z evaluated from a to b, not x evaluated from a to b. The variable here is z. So one of the things I see from time to time when I grade this stuff is that everybody nails these first few parts of the antiderivative, and then they go, oh, well, the integral of a constant, that's just that constant times x. Well, no, it's that constant times z here, because z is my variable. I'm doing the integral with respect to the variable z. So make sure you're paying attention to the variable that's being used, that's all.
Got it, thank you.
Yeah. So now we need to evaluate this between bounds of 1/4 times 2 to the 4 minus 1/3 times 2 to the 3 plus 1/2 times 2 squared minus 2. I'm plugging in my upper bound. And from that, I subtract what I get when I plug in my lower bound. Since each of these is just a power of z, when you plug in 1, you're going to get the coefficients. 1/4 minus 1/3 plus 1/2 minus 1. Simplifying stuff like this can be a bit of a headache. My advice, take care of the inputs over here, and then combine terms that already have the same denominator before trying to put together with a common denominator. That'll go faster. So I have 1/4 times 2 to the 4. 2 to the 4 is 16, so this is 16 over 4. Minus 1/3 times 2 cubed. 2 cubed is 8, so it's 8/3. Plus 1/2 times 2 squared. 2 squared is 4, so that's 1/2 times 4, or 4/2, minus 2. And then I'll distribute the negative here. So I get minus 1/4 plus 1/3 minus 1/2 plus 1. And by leaving the 16/4 and 4/2 as ratios over 4 and 2, I could easily combine them with these guys if I wanted. Or I could rewrite them as integers. Either one really doesn't matter. In some cases, leaving them as fractions can save you a bit of time. I think here I'll just go ahead and 16/4 is the integer 4. And then I've got negative 8/3 plus 1/3 is going to give me negative 7/3. 4/2 is 2. It's minus 2. I have my minus 1/4 here. The 1/3 and 8/3 I combined. Minus 1/2 plus 1. And these guys sum to 0, so let's get rid of them. I've got a 4 plus 1 is a 5. Minus 7/3 minus 1/4 minus 1/2. Negative 1/4 minus 1/2 is negative 1/4 minus 2/4 is negative 3/4. And then it's up to you again from here which order you want to do things in. We can write 5 as a ratio over 4, or 5 as a ratio over 3, or we can combine these. I think doing things like 2 things at a time is nice. 5 is 15/3. 15 minus 7 is 8/3. That's 8/3 minus 3/4. And then finally, each of these can be written as a ratio over 12. 8/3 is the same as 32/12. So this will be 32 minus 3/4 is multiplied by 3 or 3, 9/12. So 32 minus 9 over 12, which is 23/12. Yep. An important note, we used it at the start here, but I want to say it clearly because it also comes up as a good true-false problem, also can be a source of mistakes. In general, the integral of a product of two functions is not equal to the product of the integrals. explicit example here to make sure it's clear what we're saying. I'm saying that like the integral of x times e to the x dx. This is not going to be 1/2 x squared times e to the x. Right, I cannot like just integrate the x and integrate the e to the x. It doesn't work like that. Just like you need a product rule when differentiating products, you need an integral product rule when integrating products. And that's why we had to FOIL out at the start here. Okay. Let's get dirty with some trig stuff. I haven't done a whole lot of trig stuff. So I want to do the integral from 0 to pi over 3 of secant theta times the quantity secant theta plus tangent theta. Later in your math careers, you'll learn that integrating odd powers of secant on their own is a royal pain in the ass. But here we're going to get some help in the form of algebra. Because like we said, I cannot just integrate this and these separately. They're being multiplied. Differentiation here would require the product rule. So integration here would require something else. The something else that we have access to at this stage is just algebra. Let's distribute the secant theta. So I get integral 0 to pi over 3. Secant theta times secant theta is secant squared theta. And secant theta times tangent theta is just that, secant theta, tangent theta. And we put the whole thing in parentheses. We always write our integral. We always write our differential d theta. Build the good habits now. I know it sounds like I'm harping. I'm doing it for good reasons though. All right. So let's see who's had an opportunity to practice the trig antiderivatives. What is an antiderivative for secant squared theta? Think about problem 14 on the test, that logarithmic derivative when you had to differentiate tangent. The derivative of tangent is secant squared. So tangent is an antiderivative for secant squared. Same logic applied to secant theta, tangent theta, who, when I take their derivative, becomes secant theta, tangent theta.
Secant.
Good old-fashioned secant. Secant and tangent are buddies. They hang out together a lot. So this is our antiderivative, and we're going to evaluate it between these bounds. So I'll write it out. We're going to have the tangent of pi over 3 plus the secant of pi over 3 minus the tangent of 0 plus the secant of 0. And now our knowledge of the unit circle comes into play. So tangent of pi over 3 and secant of pi over 3, tangent of 0, secant of 0. You can get there by thinking in terms of sines and cosines. Tangent of pi over 3 is sine pi over 3 divided by cos pi over 3. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. Plus. You know that secant is 1 over cosine. So this should be 1 divided by the cosine of pi over 3. The cosine of pi over 3 we just said is 1/2. So this is 1 divided by 1/2. I'm going to distribute this negative. We'll have minus the tangent of 0. Tangent of 0 is 0 because it's sine over cosine. Sine of 0 is 1, cosine of 0, sorry, sine of 0 is 0, cosine of 0 is 1, so it's 0 over 1. The secant of 0 is 1 because cosine of 0 is 1. So this will become minus 0 minus 1. Root 3 over 2 divided by 1/2 is the square root of 3. 1 divided by 1/2 is 2. And minus 1 is minus 1. So you have the square root of 3 plus 1. Not too shabby, right? Let's try some more trig stuff while we're in this mindset. Let's do integral from 0 to, can I do that? No. Oh, we don't know that, do we? Okay, hang on. Yeah. This is another case where the algebraic combination of functions here is definitely not something that's going to let us just take antiderivatives bit by bit. So we got to do something with this before we have a hope of spotting an antiderivative. And again, the something is going to be some algebra. Any ideas? I'll give you a hint. It's actually very similar to the last one.
Do we separate them like sine over cosine squared and then 1 over cosine squared and go from there?
Very good, right? Sine over cos squared, that is secant tangent, and 1 over cos squared is secant squared. So this is the integral from 0 to pi over 6 of, I'll write it exactly as Shauna said, sine t over cos squared t minus 1 over cos squared t dt. And then using the, whether you call them definitions or reciprocal identities, it's up to you. But using the fact that sine over cosine is tangent and 1 over cosine is secant, I can write this as 1 over cos t times sine t over cos t minus 1 over cos t all squared dt, because 1 squared is 1. And if you look at that for just a second, you realize the first piece is secant times tangent. And the second piece is secant squared. While we're talking about trig, another kind of notation mistake I see made a lot, especially early on, especially with trig, is not writing the variable itself. It's easy to get in the habit of being like sine over cos instead of sine t over cos t. Please don't do that. Please don't do that. It's very important anytime you write a trig function that you include the variable. Without the variable, I don't know what cosine is. Cosine of t is very different than cosine of t over 2 or cosine of t squared or cosine of theta. Totally different animals. So please, anytime you write a trig function, make sure to include the variable. Antiderivative for secant tangent, we said that is secant. Antiderivative for secant squared, that is tangent. And this time we're evaluating from 0 to pi over 6. So we get a little more unit circle practice. Cosine of pi over 6 is root 3 over 2. So secant of pi over 6 is 2 over the square root of 3. Tangent of pi over 6 is 1/2 divided by root 3 over 2. That's 1 over the square root of 3. So that's my upper bound minus parentheses. When I plug in 0, secant of 0 is 1, tangent of 0 is 0. These are things you want to be fast and fluid with. Two over root 3 minus 1 over root 3. They already have a common denominator. We might as well subtract them. That's 1 over root 3. So I get 1 over the square root of 3 minus 1. I'd be perfectly happy with that as an answer. Just to be clear, the standard I'll be holding you to, you do need to get me to at least here. If you tell me this is secant pi over 6 minus tangent pi over 6 minus secant of 0 minus tangent of 0, I'll be like, that's great. No, what are those? I do need to know that you know the exact values of the trig functions at those important points on the unit circle. So decimals from calculators or leaving them as secant of pi over 6, tangent of pi over 6 can get you some stuff, but is not going to get you the exact answer. We really do want to get at least to here. Oh, sorry, I think my connection's been a little fiddly. All right, I'd like to do one more problem before I let you guys go. And that's something sort of combining the rules and tricks we've discussed so far. Do the integral from 1 to 2 of x cubed minus 2 root x plus x minus 3, all divided by x. Let's see. Cannot tell if you guys are still with me here, or if my connection has shit the bed entirely. Oh, sorry about that, guys. Looks like my internet connection's been a little sketchy. All right, here we are. We're gonna take a shot at this thing. The game is going to be to split up the fraction, just like the last one. We'll have x cubed over x minus 2 square roots of x over x plus x over x minus 3 over x. And then simplify. X cubed over x is x squared. 2 root x over x. Well, the 2 is going to come along. It's just a constant multiple. The square root of x is x to the 1/2 divided by x to the 1 is going to be x to the 1/2 minus 1, which is x to the negative 1/2. X over x is just 1. And I'll write minus 3 times 1 over x for 3 over x. So you want to do whatever, all the algebra steps you can to get your integrand into a form where you can see the antiderivative. And that means generally you want to write it as constants times powers of x. Constants times powers of x, that sort of stuff. I leave 1 over x as 1 over x instead of x to the negative 1, because remember the one exception to the power rule is the case where n is negative 1. So from here, I can see all my antiderivatives. X squared will become 1/3 x cubed. Minus 2, and then here I add 1 to the power. So x to the negative 1/2 plus 1 is x to the positive 1/2. So I'll have 1 over positive 1/2 times x to the positive 1/2. Plus antiderivative for 1 dx, that's just x, minus 3 times antiderivative for 1 over x is the natural log of the absolute value of x. So this is what's going to get evaluated from 1 to 2. I'll go ahead and there's just one piece that I can simplify a little further. 1 divided by 1/2 is 2. So this is 2 times 2 is 4. And x to the 1/2 is the square root of x. So I'll go ahead and write that like that. And now we'll plug in our bounds. 1/3 times 2 cubed is 8/3, because 2 cubed is 8. Minus 4 times the square root of 2 is just 4 root 2. Plus 2 minus 3 times the natural log of the absolute value of 2. Well, the absolute value of 2 is just 2. So that's what I get at the upper bound. And we need to subtract off everything we get at the lower bound. Plugging 1 in now, 1/3 times 1 cubed is just 1/3. 4 times the square root of 1 is just 4. 1 is 1. And 3, we have minus 3 times the natural log of the absolute value of 1. Well, absolute value of 1 is just 1. So here's the evaluation step. Natural log of 1 is 0, remember? And then everything else, I'll just start gluing bits together. I've got an 8/3 here and a minus 1/3 here. It's going to give me 7/3. I have a plus 2 here. Minus 4 plus 1 is a minus 3 here. So positive 2 minus 3, that's minus 1. I've got a minus 4 root 2 minus 3 natural log of 2. And that's everything. The 7/3 and the 1 are both rational numbers, so it might make sense to put them together. 7/3 minus 3/3 would be 4/3.
Did you already distribute the negative?
Oh, good question. So I hit this guy with his negative. These two make a -3, but then this negative would be positive. You caught me just before it propagated. Yeah, so this would be a 5. Thank you. Thank you. So this, instead of a 4/3 here, we'd have 7/3 minus 5. That's 7/3 minus 15/3. And that is 8/3, negative 8/3. Very good. And then minus 4 root 2 minus 3 log 2. Yeah, thank you. Good catch.
I hate to do this again. Wouldn't it be a positive 5? Because you made the 3 a positive plus 2.
Oh, yes. Yes, yes, yes. Yes, it is. Oh, and that's going to change this again. All right, let's try one more. 3rd time's the charm. So 7/3 plus 15/3 is going to be 22/3, right? And then minus our 4 root 2 minus 3 natural log 2. Okay, apologies for being sloppy. It's a teachable moment. There's a lot of stuff to do here, right? There's plenty of room for little mistakes. I will not tear you to pieces over little mistakes. Definitely when I test you, I'm looking to see that you know the calculus. So an arithmetic mistake, if it's one small one, I might not take off any points. If it's a large arithmetic mistake where there are several, taking off a half point or a single point out of 10 is usually around the scope of things. But try to be careful. Try to be careful. All righty. Any lingering questions before I let you guys go for the day? Okay, then I'll go ahead and wrap up the meeting here. Please work hard on that homework set over the weekend. When you come back on Monday, we're going to talk about the net change theorem. So this section 5.4 in the textbook is on indefinite integrals and the net change theorem. Indefinite integrals aren't anything special. As we mentioned the other day, it's just a new notation for antiderivatives. But the net change theorem is a neat thing with some cool applications and a little bit of subtlety. Then the rest of next week, we're going to spend learning something called U substitution, which is the backwards chain rule, right? It's like the integral version of chain rules. That section tends to be a little bit tricky. So we're going to spend more than one day on it, but probably not more than 2. It would definitely be in your best interest to have the homework completely done by Monday so you can focus your attention on that stuff. If there's anything you need to talk to me about, come see me in office hours or shoot me an email or a Canvas message. Otherwise, I will see you guys on Monday.